So hello, welcome to another class. Today we're going to start chapter 10. Just on the record, there's only 12 chapters. So we got this chapter and two more. I would like to start talking about the final in more detail, but the school hasn't made a final exam schedule yet. I might still talk about the final a bit more. I think I have it planned to talk about at the end of this chapter. Yep, I do. I just checked. Um, but I don't know the dates yet. So that's fun. Hopefully I'll get that soon. Um, but in general, today's chapter is about vibrations and waves. That we're going to talk about things like springs bouncing up and down, and pendulums swinging back and forth, and then other type of waves, which I actually forgot to prep for, but we won't get to that part till Wednesday, anyways. Before I get started, I am once again moving an office hour. I apologize. I have way too many meetings. My office hours on Tuesday are normally 2 to 3:30 this week, and as of now, only this week, I'm moving it to 1:30 to 3 because I have to go to a meeting at 3. So it'll really be like 1:30 to 2:50 so I can prep for that meeting. If you are planning on seeing me between 3 and 3:30, let me know. I'll make some other time to meet with you. Okay? Let's get into it. In chapter 5, I introduced something called Hooke's Law that said anytime you take a spring, and if you take the spring, and let me put this guy up here, and if you compress the spring, actually I'll zoom in a little more. If you compress the spring, or if you pull the spring out like so, anytime you do either with a spring, there will be a force. And the force acting on the spring will go by negative kx. The negative sign I'll come back to, but K is the spring constant of the spring, how springy it is, and X is how far you push it. If I got a new ruler because we broke the last one in class. If I take this and push it in 2 centimeters, because that's how far this is, that would be what X is, how far I pushed it. If I pull this out 1 centimeter, that's what X would be, 1 centimeter. What's of note, though, is that negative sign. That negative sign represents that X and F are always in opposite directions. If I pull Mario to the right, the force is to the left. If I push Mario to the left, the force is to the right. That it's always X and F are always in opposite directions. See, because of that, what it means is the force will always push the thing back towards the equilibrium. Because, yeah, you push it to the right, the force is to the left. Push it to the left, the force is to the right. And for that reason, it is often called a restoring force because it wants to restore to equilibrium. That anything you do to take it out of equilibrium, it's like, screw that noise, I'm going back there. Okay. Which, do I have a video on Hooke's Law? I do. Right now I have here is two different springs. These springs have different spring constants. And so I'm going to hang weight on both of them. What you can see is once this settles, is that they stretch a different amount. They stretch different amounts. I'm adding more mass. They stretch different amounts because they have a different spring constant. And so, yeah, that's why they stretch different amounts from going from heel to heel. Okay. But this is the negative sign. What's important here is that if X is positive, F is negative. If X equals 0, F is 0. And if F is negative, F is positive. This is going to be important. Because what we want to talk about in this class is not, we talked about this before, just pushing the spring. We want to talk about what happens when you pull the spring and let go. That if instead of just putting the weight on it and letting it be, what happens if I push it downwards and let go? And what you'll find is that the spring will bounce up and down, like so. And what we're going to do this chapter is talk about the physics of that, this motion, it bouncing back and forth. Okay? So, let's say I take a spring and I pull it at distance A and release from rest. What's going to happen? And you know what? I have this GIF going on here, but let's instead just do it with this guy. So it's going to start at rest. I put it at distance A, and then I let go. What happens is once I let go, I pulled it down a distance A, right? What's going to happen is there is a force upwards. I pulled it down, so there's a force upwards. And what's going to happen is it's going to accelerate upwards. And I pulled it down, had it at rest. When it accelerates upwards, what's going to happen is V will get bigger and bigger as it goes up. And what will happen is on its way up, it'll accelerate upwards till it hits the equilibrium. At the equilibrium, F equals 0. But once it hits the equilibrium, there's no force. That means there's no acceleration. But it had velocity. It had velocity because it was already moving. It had upwards velocity when it hit that spot. And so what happens is it shoots, oops, let me just pause that, is it shoots past the equilibrium and rockets above it. That its momentum causes it to travel above our equilibrium position. At this point, what you get, here they are, is that this thing is rocketing upwards, but now it's above the equilibrium. So acceleration is now downwards because the force is downwards. And what that's going to cause is that the force and the acceleration, the force and the velocity are in opposite directions. So it'll slow down. And it will go slower and slower and slower until it's a distance away from the equilibrium equal to how far I initially pulled it. That if I pulled it down at distance A, it'll go up to a height A. And once it hits that height A, what's going to happen is at that moment, its velocity will be 0. But it will still have an acceleration pointing down. And since it still has an acceleration pointing down, I'm writing this backwards as I'm saying it. But since it still has acceleration pointing down, it'll be the same as if I throw something up in the air. At the highest point, it'll have no velocity, and then the force will push it down. And it will go down and through the 0. And will go on indefinitely. That what I can say is anytime it's lower than the equilibrium, there's a force up. Anytime it's higher than the equilibrium, there's a force down. But the velocity can be up or down depending if you're above or below, if it's going up or down. But it will bounce back and forth between 3 major spots. The amplitude A at the top, or at the top your height is A, your force is a maximum, your velocity is 0. The middle, at which point your position is 0 and your force is 0 and your velocity is a maximum. And the bottom, at which your x is negative A and your force is a maximum and your velocity is 0. Any questions though?
So the indefinite part of the acceleration, was that due to momentum?
Basically, it's because once it hits the middle, right? Let me see if I can pause. I got pretty close. I'm never going to get it. But what right in the middle has no force, but even though it has no force, it's traveling upwards, right? I mean, I could break this down to 4 categories. And here, you know what? Let's notepad.
I can't unmute myself.
So I can break this down to 4 categories, right? There is, or I can even more than that. So let's say this is when it's not stretched at all, right? So there's when it's at its lowest point. There's when it's on its way up. Equilibrium, on the way up, highest point. And then going down, equilibrium. And I'm going to say this right here is the equilibrium. On way down, lowest point, right?
Mm-hmm.
So for each one, I can define velocity and force/acceleration. And I'm going to just color code this. Anytime it's below the point, the acceleration is upwards. Right? And anytime it's above the equilibrium, the acceleration is downwards. Well, the further away, the bigger it is. That at these edges will have a much larger acceleration than these other points. But as for velocity, velocity is going to be changing. See, at this point, its velocity is 0. Here it has an upwards velocity because I had an acceleration. And what happens when you get to this point is it's going to have a larger upwards velocity. But since there's no force acting on it, the velocity won't change. Well, then it will start moving up, going slower and slower and slower until all of the acceleration cancels it out. And now there's a force down, so now it'll go downwards, downwards, downwards. Does that help explain it?
Yeah, yeah.
I should make that in a slide in here. And as long as in the real world, this doesn't last indefinitely, right? If I do this, eventually this spring is going to stop. That's because of friction within the spring and the molecules of it. Then in the real world, it's not indefinite. But that's because of damping. And we're going to ignore damping for now. Now, because this motion keeps going, anytime you have motion that follows this idea, that the net force is along the direction of motion due to Hooke's law, this is something called simple harmonic motion. Simple because we're ignoring damping. We're ignoring the actual things going on. We just have an ideal spring. We're saying the spring doesn't weigh anything. It's just a mass on a spring that's just bouncing. Harmonic because it's just this repeating back and forth pattern and motion because it's moving. And we can define a few terms. The first of which is the amplitude. Your amplitude is how far you get from the equilibrium. That from here to here, that's the amplitude. And however far down it starts, that's how high up it goes. Of note, this also works side to side. I'm just not doing side to side at the moment. We can also define the period. The period, which uses the symbol capital T, is how long it takes in seconds to go from one spot to return to the same spot moving in the same direction. How far it takes it to go, from x equals a to x equals negative a back to x equals a. Then if I wanted to find the amplitude, not the amplitude, the period, I'd say it starts here and I would just time how long it takes it to go up and back down. That's the amplitude. Sorry, that's the period. To go from lowest to highest to lowest again. Or you could say from highest to lowest to highest again. It's just how long it takes to complete one cycle. Of note, you can really see here, the way these lights are going, that the acceleration is constantly changing. Keep that in mind. I'm going to come back to that idea. The thing is, period is easy to measure, right? I can just take a stopwatch, say start stopwatch, start stopwatch. But period is not normally what we need. There's also something called the frequency. The frequency, which uses the symbol F, is the period is how many seconds in one cycle. The frequency is how many cycles happen in a second, where frequency is by definition 1 divided by period. And so yeah, 1 divided by t, that's frequency, which has units of hertz, where a hertz is an inverse second. Okay. Now, let's talk about this acceleration when this happens. Newton's second law, right? That if I ignore the mass of the actual weight hanging, let's say we're going side to side, so the only force is the force of the spring, there's a reason I can ignore the weight of this guy when it bounces up and down. But for now, I'm not going to get into that quite yet. But let's say when this bounces up and down, the force that's causing it to move is the spring. That when it's up, the spring pushes it down. When it's down, the spring pushes it up. So I can say the force of the spring is the only force. And so F equals ma, the force of the spring equals ma. If I rearrange this, I can solve that the acceleration of the spring will always be negative k over mx. That the acceleration is a function of position. That the acceleration is not just a set value. Actually, I'll go to this guy. But it's constantly changing. That the acceleration is a maximum here in the upward direction and a maximum here in the negative direction. And that is everywhere else is changing. And it's a maximum here also because that's the same spot. That the acceleration keeps changing. And so all the kinematic equations we did earlier, they all assumed acceleration was constant. But since acceleration is not constant, we can't assume acceleration is constant. That's a really dumb sentence. Acceleration isn't constant, so don't assume that it's constant. So we can't use the kinematics. So we need our own special equations of motion just to describe this madness. Now, I want to say something before I go further. I'm doing this all for a spring. Really, anything that has a force that's always in the opposite direction of motion can be treated as one. The shock absorbers on a car, old cars had springs, new ones don't. But you can treat it like a spring because it's always bouncing back in the same direction. If someone's just bouncing up and down on a diving board, treat it as a spring. You strum a guitar string and it bounces back and forth, you can treat it as a spring. This is anytime the force and the motion are in opposite directions. Now, if we want to make equations for this, we can do it in a bunch of different ways. And let's start with the one we've already covered. If I have a spring, if I stretch a spring, I give it potential energy. When I let go, it turns into kinetic. We did all those problems, right? Where Mario went, pushed down on a spring, caused him to go shooting up in the air. He did not shoot up in the air at all in that. We did this problem in class multiple times in chapter 5. That if you compress or stretch a spring, you give it potential energy. Well, the potential energy due to a spring is 1/2 kx squared, right? Well, we can use this potential energy to try to figure out what the spring is doing. Because if I go back to that drawing I had over here, I know it's on the screen, we can say at all points energy is conserved. And let's say you have a horizontal spring. It's just bouncing back and forth side to side. We can say at all points has a certain amount of energy. The energy is going to be 1/2 mv squared plus 1/2 kx squared. And at all points, that's the same. If you got a vertical spring up and down, you're going to have to include gravitational potential energy also. I'll do one horizontal a little bit, but that does add another level of complication, this MGH, that we're going to ignore for right now. And there's a bunch of reasons why I can. But for the for the horizontal spring, I can say at the amplitude, V equals 0. So at the amplitude, all of the energy is potential, where your X is going to be capital A because it's the amplitude. At the equilibrium, your X equals 0. So at equilibrium, all your energy is 1/2 mv squared, where V is going to be a maximum. And conservation of energy says the energy is the same everywhere else. And so the energy at the amplitude equals the energy at the equilibrium equals the energy everywhere else. And this right here, this conservation of energy equation, this will tell you exactly what the velocity is as a function of position. Anytime you need to know velocity as a function of position, this is how you get it. Conservation of energy. Questions?
Could you remind us real quick? I know that this is the conservation of energy equation,
Yep.
but if it was super important that k was negative, why it's plus 1/2 k?
K is not negative. K is a positive number. The equation is that F equals negative kx. That's the equation for force. But the equation for potential energy does not have a negative sign in it.
Okay. Okay.
And the reason for that negative sign is because it's a vector, right? Force is a vector. And they say force is in the opposite direction as x. But keep in mind, potential energy is a scalar. Energy doesn't have any vector components. So it doesn't need the negative sign because it doesn't have a direction.
Oh, okay. Okay. I'm with you.
Okay. I will say if it's going up and down, you can actually still kind of use this equation. The reason why, and if I go back to the first video, basically what gravitational potential energy does is that's going to change where my equilibrium is. I'll stop right here. That with this no mass hanging on it, that's its equilibrium. With this mass hanging on it, its equilibrium is now down there. And I can do the motion based off this new equilibrium. That if I go and add more mass, let me put that on. If I add more mass, that's just going to change my equilibrium to that point instead, and so on. And so you can normally get away with this, but really you should only use this for horizontal springs. For vertical springs, you should include gravity. But I can ignore it for some reasons for that. Okay? Okay, here's a neat thing. Let's say I go back to this bouncing, right? And let's say while it's bouncing, I go and I attach a pen. and I glue a pen on it, right like this. And so while it's bouncing, there's a pen going up and down. And as that pen's going up and down, I just drag a piece of paper across. If you do that, what you get is that when this bounces up and down, if you plot basically its height as a function of time, you get this nice wave. And what it is it matches perfectly a cosine wave. That at all moments in time, your position is a cosine of omega t. Now, I'm going to come back to omega. Well, I'll start the omega stuff now. But a few things. First off, omega is defined as angular frequency. Well, angular frequency is 2 pi times the regular frequency. And so we can say position is a function, once again, conservation of energy, velocity is a function of position. But if you want position as a function of time, you'll use this equation, where omega is 2 pi f. Okay? This does assume you're starting the stopwatch when it's at the amplitude. One thing about this, I'll get into that one thing in a second. Let's stick to the order of my notes are in. Now, we've already used omega for equations. 2 chapters ago, we said omega was angular velocity, right? Angular frequency has units of radians per second. Angular velocity has units of radians per second. Angular velocity is omega, angular frequency is omega. This is all not a coincidence. The reason why the same symbol is used with the same units is that if you look at a wheel and try to look at its angular velocity, and as something is spinning, as shown to the right, you plot its position in x and y as a function of time. What you can find is that if you look at the x position or the y position of something spinning, it also makes the same wave. And what people realized is that when something is rolling, that it's the position, the x position of something. So once again, we're not talking about something moving across, but we're just saying this guy is here, then 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 here. Just its position in x, which is going this way, then back, then this way, then back, then this way, then back, actually goes by the equation x equals a cosine omega t, where a is the radius of the circle and omega is the angular velocity. And people are like, you know what? With a spring, with a pendulum, it matched the equation. And so people define angular frequency using the same symbol as angular velocity because it can be used the same. How we understand simple harmonic motion is treating it as if it is something spinning. And so angular frequency uses the same symbol with the same units as angular velocity on purpose. And we'll say, once again, that the position of something bouncing up and down is the amplitude times the cosine of the angular frequency times time. Well, angular frequency is 2 pi f. And keep in mind, I said the period of motion is 1 over f. That means the period of motion is 2 pi over omega. Questions? Sorry, I'm going to do something real fast on that slide. There's a random drawn circle. Any questions why I try to find this stupid circle and delete it? Why? No. I can't get it. Okay, I give up. I'll do it later. I don't know what that circle is. Okay, so here was position as a function of time. If you want position as a function of time, x equals a cosine omega t. Well, omega is angular frequency, a is amplitude, lowercase t is time. We can also use this to get velocity as a function of time. Now, how I do this, how I get velocity as a function of time, the answer is some calculus happens. So you can ignore the process. Those of you who know calculus, I'm taking a derivative, and I can find velocity as a function of time. Velocity as a function of time is given as negative omega a sine of omega t. And with some more calculus happens, I can also find acceleration as a function of time. That acceleration is negative omega squared a cosine omega t. Although if you take a look at this, you can see that x equals a cosine omega t, and I have an a cosine omega t term here. So I can just say that acceleration is negative omega squared x. And that'll be position, velocity, and acceleration as a function of time. If you want velocity as a function of position, you're going to have to use conservation of energy. If you want acceleration as a function of position, well, there you go. We just covered it right here. If you want position, velocity, or acceleration as a function of time, you can use these equations. Quick question for you guys. Sine of anything. Just sine of an angle. What's the largest sine of an angle can ever be?
90.
Not the angle. What's the value? Like, what is the sine of 90?
1.
1. What's the smallest it can ever be?
0.
Nope. -1.
-1. Right.
Yep. So what that means, since sine and cosine both go from 1 to -1, that means the maximum value you can ever have of acceleration, will be negative omega squared a. Oh, sorry, will be omega squared a, because it will be when it's -1. And the maximum value you can ever have for velocity will be omega a. Just so you know. Okay. Questions so far? Okay. Before I go further, these equations all have the cosine of omega t, sine of omega t, where omega is radians per second, right? So if you do the cosine omega t or the sine of omega t, you're going to do radians per second times seconds. So omega t is in radians. For this chapter, and only this chapter, your calculator must be in radians. Doing problems from any other chapter, you want to be in degrees. This chapter must be in radians. I will go one step further. I always make a point so that these equations here, I always make it so they never show up on the final. The reason why is because I think it's mean if I had one problem your calculator had to be in radians and everything else in degrees. I will not put these problems in radians or these equations on the final, so your entire final will be in degrees. But on the homework for this chapter, put your calculator in radians. Okay? Okay, so let's go further with this, with what I'm trying to get to. So we got a spring bouncing up and down. And it really should be left and right because I didn't include potential energy, but you know, this is the figure I found, so we have to deal. Energy at all points, kinetic plus potential. I'm ignoring gravitational potential. Let's say it's going side to side. I already said at V max, x equals 0. At that point, that means energy is just 1/2 mv max squared. At your amplitude, the maximum value of x, v equals 0. So at that point, your energy is 1/2 ka squared. What I'm going to do is say conservation of energy says these energies must equal each other. I can multiply both sides by 2. Now, V max, I already said that if we look at up here, V max is omega A. So I'm just going to say V max is omega A and say that means 1/2 A omega squared equals Ka squared, which I can factor through my squared, divide both sides by A squared, divide by M, and square root. And this is kind of interesting. This tells you that omega is the square root of K over M. Keep in mind, omega is the angular frequency. Omega was directly related to how fast it bounces. And this tells you what omega will be for a spring, knowing what is the spring constant and how much mass is hanging off it. It is not the mass of the spring. This is assuming a massless spring, but how much weight, if I go back to my video, how much weight this accelerometer is. What is the mass of that accelerometer? That is what that tells us. For the record, I also could have said F equals negative kx. So negative kx equals ma. So acceleration is k over mx. But I gave these equations where I said a equals negative omega squared x. If I plug a equals negative omega squared x into that equation right there, I can cancel out an x and get the exact same value. I could get this in multiple ways. And what this says is that the angular frequency of any spring with a mass hanging on it, which is 2 pi f or 2 pi over t, will go as the square root of k over m. And rearranging it says the period of any mass hanging on a spring will be 2 pi square root of m over k. That if I'm going to make this smaller. What I have here is two springs with the exact same mass, but they have different spring constants. If I set them oscillating, you can see that the period of motion is not the same. Let's go to where they're both going. But I can say on this right guy, the period of motion is 1 Mississippi. It's like 1 second. The period of motion on the one on the right, 1 Mississippi 2, is also the 2 seconds. That by changing k, I've changed the period of motion. If I instead take two springs, these springs both have the exact same spring constant. But what I did is I changed the mass on them. That now the one on the right has less mass. And if I set them oscillating, you can see these also don't have the same period. That the one on the right is going faster. That's because mass and spring constant would decide what the period is. What doesn't decide the period is amplitude. And I stupidly did not film an amplitude one for this. So I apologize for that. Though I might be able to do it with the slinky. That if I take this and put it down, let it bounce, I can time how long it takes to go from the lowest point to the highest point. And go 1 Mississippi, about 1 second. If I go real big, 1 Mississippi. Oh, it doesn't, because it hit, it didn't go the way I said. Let's see if I go smaller. So it's going as small. Here, I'll get closer. 1, 2, 3, 4. It's at about a second. If I go bigger, 1, 2, 3, 4. Period's exactly the same. The period has no effect on, the amplitude has no effect on the period. It doesn't matter how far you pull it, and this when it goes real big, it does because it hits the top and it messes it up. But as long as it doesn't collide at the top, that the amplitude is the same for this period as the period is the same for this amplitude. That period and amplitude have no effect on each other. The only thing that matters is the mass and the spring constant. Okay? Questions? Okay. Let's do an example problem. This one was part of This is part of this was an old final question, but there was other things going on here. I think I added parts and changed some parts, so it's not really an old exam question at all anymore. But let's say we have a 15-gram bobblehead doll, and the head of the doll is 15 grams, and we set it bouncing, so it's just bouncing up and down. As it bounces with a period of motion of 0.25 seconds. A, what is the spring constant? B, if we give it an amplitude of 2 centimeters, what's the maximum velocity? C, what is its velocity at 12.2 seconds? And D, what is its velocity at 1.29 centimeters? If I want to solve these, I'll start with A. What's the spring constant? Well, I said a period of motion. Well, before I get into that, 15 grams is 0.015 kilograms. And I said a period of motion of 0.25 seconds. Period of motion is directly related to m and k. As I said before, the period of motion is 2 pi square root of m over k. I can solve this for k. What I'll do is I'll divide both sides by 2 pi. I will then square both sides. When I square both sides, I square everything. T becomes t squared, pi becomes pi squared, and 2 becomes 2 squared, where 2 squared equals 4. Now I want to solve for k, but k is in the denominator. So let's get k out of the denominator. I'll multiply both sides by k. I can now multiply both sides by 4 pi squared and divide both sides by t squared. And the period of motion will just be 4 pi squared m over t squared, to which I can plug in some values and get the spring constant. Any questions there? Part B. The head is pushed 2 centimeters and released. What's the head's maximum velocity? Pushed 2 centimeters means its amplitude is 2 centimeters, or 0.02 meters. You want to find the max velocity? I mean, I can find the max velocity a bunch of ways, but I earlier said that V max is omega A. And omega, I can either say omega is 2 pi over t, or I can use the square root of k over m. Doesn't matter which I use. I usually use 2 pi over t because when I have to square root stuff, I sometimes forget the square root. So I'll just say omega is 2 pi over t, which is 25.13 radians per second. And so V max is just omega times A. There's the value. Any questions here? Okay. Part C. What's the head's velocity at 12.2 seconds? If I give you time on these problems, if you know time, use the sine cosine equations. We know the time. So I'll use the velocity time equation. V equals negative A omega cosine omega t. Now just plug in. There's the velocity. Negative 0.139 meters per second. It's negative because it's moving down. Okay. How about what is the head's velocity when located at 1.29 centimeters? If I do not give you time, if I ask for velocity as a function of position, use conservation of energy. That the energy at A equals the energy at X, which is potential plus kinetic equals potential plus kinetic. Now, what I can do is I can say I know V max. I have two choices. I could either set this equal to the energy at the amplitude, where the energy at the amplitude is 1/2 Ka squared. Or I could set it equal to the energy at the equilibrium. I chose to set it equal to the energy at the amplitude. And say at the amplitude, the energy is 1/2 Ka squared. And the velocity is 0. And so 1/2 Ka squared equals 1/2 Kx squared plus 1/2 mv squared. I can multiply everything by 2. And I get this. Subtract both sides by Kx squared. Divide both sides by m. And square root. I can plug in and get a value. Now it's of note there's two possible values. Because when x is at 1.29 centimeters, it could be going up, it could be going down. It could be going left, it could be going right. We don't know that. Because it at some point goes both, right? That any given height, it might be bouncing up or down. We can't tell. But if I ask for velocity as a function of position, conservation of energy. If I ask for velocity as a function of time, or acceleration as a function of time, or velocity as or position as a function of time, use the sine cosine equations. Questions?
This example to me seems like one of the conservation ones where it should include MGY.
Yes, it probably should. Normally with a bobblehead though, you don't bounce up and down as much as it kind of goes back and side, which is why I didn't include it.
Okay.
You'll find most of the palms I do side to side. Like, yeah, if you hit a bobblehead, like you don't really like pull it up. You just kind of push it to the side and watch it bounce. So I was viewing this as a side to side. I should have actually written that explicitly. Do I? I do have a bobblehead. So I was saying it was kind of doing this. Except this has damping, so it's going to stop, but just bouncing back and forth.
Got it.
A random Han Solo bobblehead. Oh shit, that just fell apart. He fell off his base. Okay. Okay. This was all for springs. But let's look at something else. What I have right here, or at least that I'm assembling, is a pendulum, right? Ignore this part of the string. If I have this pendulum, if I pull it to this side, it's going to go to the middle. If I put it to this side, it's going to go towards the middle. This also is using the same logic. And so let's look at pendulums instead. See, what happens when you have a pendulum? When you move the pendulum to the side, I'm going to go and look at this in terms of a tilted coordinate system. What I'm going to say is I can define at any spot as x along its motion and y straight up in the direction of the tension. This doesn't seem very logical because it means as this spins, your coordinate system is going to be moving. But let's for now say we're going to use a coordinate system like that. It's going to be obvious where I go in a little bit. What happens when I do that? Is I'll say tension is in the positive y, and gravity has two components. One component of gravity counteracts the tension, and one component of gravity is what pushes it on the path. And that anytime you set the pendulum to one side or another, there will be a component that keeps it on this circular path, which is going to be mg sine theta. Sine ends up cosine for the same reason as a ramp. It's a tilted coordinate system, and theta being the angle the pendulum's at. There is something called the small angle approximation, which says if you're working on radians, anytime your angle is small, the sine of theta is approximately theta. The small angle approximation says for small angles, sine theta is equal to theta. And we're going to use this here. That being said, everything I'm about to do with pendulums doesn't really work for huge angles, only works for small ones, like this much. But that's okay because that's the most common thing, and honestly, it gets pretty close for big angles too. Now, keep in mind, we have a definition for arc length. Arc length equals all theta. And so what I can say is that in this case, the distance x, how far it is from the equilibrium to oval, is going to be all theta, but all is the length of the pendulum. Which means rearranging the angle is x over L. And I'm going to plug that in for theta in my equation right above it. And so that means the force at any point is negative mgx over L. Or to write it differently, the force is negative mg over L x. And I'm about to do one of the craziest fucking things I ever do in physics in this class. You see, for the spring, we said for a spring, F equals negative kx. And for a pendulum, we're saying F equals negative mg over Lx. And so what people realize is, you know what? Springs, pendulums, it's the same thing. You got a pendulum, just pretend it's a spring. Pretend it's a spring that has a spring constant of mg over L. Is it a spring? No. Does it have a spring constant? No. But let's just pretend it is a spring with that spring constant. And if you do that, the math works.
That's so whack.
It kind of is. So when we had the spring bouncing back and forth at the amplitude, its position was a maximum, its acceleration was a maximum. For a pendulum, same thing is true. In equilibrium, you had no force and no velocity, the same thing is true. That when a pendulum goes, I don't want that one yet. Where is, for a pendulum, when it goes bouncing back and forth, we can see that the acceleration always points towards the equilibrium and is changing as a function of time. And it just follows the same logic. And so, yeah, I set this going. It's the same as in a spring. It's bouncing back and forth. Okay? Now note, amplitude is the maximum it goes. If you set a pendulum going, it'll never go further than the amplitude. That if you take this thing and start with it right up against your nose, let it go, let it come all the way back, it'll come right back to your nose. Amplitude is, I like this version of this pedal. Someone animated it. Amplitude is the max. It can never go further. Okay? So what we're going to do is we're going to take all of our equations for a spring, and we're going to say all of our equations for a spring, let's just plug in K equals mg over L. And that'll give us the period of motion for a pendulum. That for a pendulum, the period of motion is 2 pi square root of L over G. That is how long it takes the pendulum to do one period. Just because all I'm doing is taking this value right here and shoving it in. We're going to initiate the equation for frequency and angular frequency. And there you go. Period of motion of a pendulum. Now this assumes a simple pendulum. This assumes a massive thing on a weightless string. This is not going to be something complicated. Like if I have this pencil going back like this and the mass is spread throughout it, that's getting a little more complicated. But it's a string, so like this guy, with a mass on the end. Okay? Here's the crazy things about this. The period depends only of the length of the string and what planet you're on. The period is independent of mass and length. Oh, sorry, mass and amplitude. Sorry, not length. Take, for example, if I take this ball and I give it an amplitude of this fall. Oops, I went too fast. Give an amplitude this much. So here's our amplitude, right about here. I can time how long it takes it to do one period. 1 Mississippi 2. Right? 1 Mississippi 2. 1 Mississippi 2. If I move it up to here and give it an amplitude, oops, and give it an amplitude that much bigger, if I time how long it takes, 1 Mississippi 2, 1 Mississippi 2, 1 Mississippi 2, 1 Mississippi 2, that every time I change the amplitude, it has no effect on the period. It doesn't matter what the amplitude is, the period will be the same. Period only depends on length. Likewise, it has no effect on mass. If I was to remove that ball and add a ball of a different mass, which I'm sorry I did not record me doing, I apologize, it would have the exact same period. It's only how long it is. Any questions with that? Okay. I'm going to, I got 1 minute. So I don't have enough time to do my next slide, so I'm just going to stop there. And we'll pick up Wednesday, where I'll go a little bit further on pendulums, and then start talking about other types of waves, and talk about playing guitars. So, yeah. Have a good day.